So the first question you have to ask yourself before you start an analysis is, which software package should I use? And this is a question which has naturally become harder to answer as the field has developed. So here I'm showing what are probably the three most popular packages: AFNI, FCell, and SPM. However, today we have a variety of packages we could feasibly run our analysis pipelines through. And what I want to get onto with this is this concept of analytic flexibility. And what this is about is, when you have got many acceptable methods you can use in an analysis, we need to be somewhat vigilant of the variation in the results we can get from these methods. And I think this is something which is so relevant in neuroimaging, where we do have lots of choices we can make in our analyses. And areas where this has already been studied is in choices of your analysis pipeline, choices of software versions which are changing all the time, and even operating systems which can have some sort of effects on your final results. But what could be more fundamental than this first decision? What impact does the software package have on your analysis results? And to start you thinking about this, the actual statistical parametric mapping method that Carl Friston has introduced for analysis of functional data is based on mathematical principles which really should be implemented identically across these packages. So in that sense, we would really hope to see some similarities here. Now, I've prepared for a little bit too long, and I want to have some questions, so I'm going to move on from some background. But the study we've looked at to look into this is that we've taken 3 published MRI results, and what we've done is we've run them through AFNI, FCell, and SPM. But importantly, we're trying to implement the pipeline that was done in the original publication. Now, in addition to this, we have also used parametric and non-parametric, i.e. permutation test inference methods. So at the end of this, what we get is 2 sets of results for each software package for each publication we've looked at. And then what we've tried to do is devise some quantitative methods so we can compare not only our results between software packages, but also comparing these 2 inference models, and finally to go back to the original publication and look at the figures from those publications and see if the results we've got coincide with this. Now, although I've already said we wanted to replicate the original analysis, our main goal here is to look at differences between software packages. So before we started this study, we determined some fundamental steps to ensure that our results were comparable. And these are commonly known best practices. So we decided that we would always use brain extraction of the anatomy. We would always use nonlinear registration to M&I space for the functional data. And we would always use 6 motion regressors in the GLM. So these are practices that all of these software packages would advocate. So now that's the setup. For the rest of the talk, I want to talk about the results from this study. And I think the best place to start is to look at the group-level thresholded t-statistic maps. So here's the replication of the first study we did. So this was a balloon analog risk task with 16 subjects. And on the right-hand side of this slide, what you're seeing is the thresholded maps at the group level for the main contrast from the original paper. And immediately when you look at this, you do start to see some similarities. So, for example, this big cluster of activation in the anterior cingulate at the front of the brain has been captured in nearly all of these packages and inference models. And as well as this deactivation in the ventromedial prefrontal cortex has also been captured. However, when you start to look closer, there are some very clear differences as well. So to begin with, to draw your attention to the AFNI parametric and permutation results at the top, what we see is that AFNI parametric here has been more liberal in the sense that the t-statistic values are higher for this significant activation. Now, the real elephant in the room in this study is this F-cell permutation result, where no significant activation has been found. So what we did is we looked further into this, and to understand what's happened here, we actually have to look at a coronal slice. And just to highlight what's gone on here, what we've actually seen is a facet of cluster-wise inference, where if you have one big activation cluster which splits into smaller clusters, this can cause these clusters to be deemed insignificant. So in the F-cell parametric result here, this activation we saw in the anterior cingulate actually covered multiple regions of the right hemisphere of the brain. And then when we did this study with the permutation inference, this cluster broke up into smaller clusters and was therefore deemed not to be significant. Now, moving on to the second study we looked at, this was a false belief task with 21 subjects. And here, looking at the thresholded maps, we seem to have an even better degree of similarity in the sense that we've got these activation clusters in the ventral medial prefrontal cortex, as well as the temporoparietal junction at the back of the brain. And we've captured that in all these software packages and inference models, as well as what was originally seen in the publication. But when we looked further into this, we found this wasn't the full story. So here, in fact, only AFNI and FCell determined any significant deactivation, whilst SPM only found significant positive activation. So we really wanted to analyze further into the disagreement we were seeing between locations of activation across these software packages. And the way we've done this is by using the dice similarity coefficient. So for the rest of this talk, I'm only going to look at the first study we've replicated. And here I'm showing the dice coefficients for the positive activation clusters. And immediately I want to draw your attention to the top left-hand side of this slide. So this is comparisons across software for the parametric inference models we've used. And what's striking here is that the highest dice coefficient we found is 46.5%. So what that's saying is that in all three of these software packages, of the total volume of clusters that was reported in both packages, less than half of that volume was shared between the two software. And when we looked at all of these studies, the highest dice coefficients we found were less than 60%. So when we looked at this second study, and we did see some similarities, I think what these dice coefficients are conveying is the level of detail we missed when we just look at slices of our results. Now, as I've already discussed, for F-cell permutation in this study, there was no activation. So here the dice coefficients are all 0. But if we look at the comparisons of the two inference models within each software, we have higher dice coefficients, which suggests some level of coherence between these two inference models on the locations of activation. So now we've looked at locations, we wanted to move on and look at differences between the magnitudes that were being reported. And the way we've done this is to use pairwise comparisons of the unthresholded statistic maps using Bland-Altman plots. And what I'm showing here is the Bland-Altman for again, the parametric models across the three software packages. And across all three of these plots, what we're seeing is a cloud of points. So that's a great spread in the x-axis, and more importantly, a great spread in the y-axis, which means that there was large differences between these packages in the t-statistic values they were reporting. Now, the symmetry of these clouds really show that we can't say that one package was more liberal than another. And in fact, there's this more random disposition between these packages. And the way I've shown that is with this ellipse on the AFNI and FCell plot. And this is what you'd expect to see if these were two completely independent data sets being compared. So just to reiterate that, what we've done is we've put the same data and tried to do the same pipeline in each of these three packages, but these clouds we're seeing can be compared to what we'd see for completely independent data. Now, looking at again, this is the comparisons between the two inference models. For SPM, what we see is a perfect Bland-Altman plot. And the reason that is because SPM uses the same ordinary least squares method to get its unthresholded statistic map for both parametric and non-parametric inference. However, for AFNI and FSL, although we see something a bit worse, the tightening of these points towards the x-axis shows a greater level of agreement than the cross-software plots I showed before. The final method we used was Euler characteristics, and to summarize what this does, a way you can characterize the Euler characteristic is that it calculates the number of clusters minus the number of handles plus the number of holes in a thresholded image. So for high thresholds, what we expect is just to see clusters. So here the EC is just giving you the number of clusters. But for lower thresholds, what the EC is doing is giving you a topological signature of the images. So what we've done is we've thresholded our images over a range of t-values, and here I'm showing the oily characteristic plots for parametric and non-parametric inference. And in particular, I want to highlight for higher thresholds where we should just be seeing the number of clusters, these curves are not converging in a sense. So there's still a large degree of difference in the number of significant clusters being reported. And finally, the red line I've drawn this is the t-value that was used for the original study. And what we're seeing for non-parametric is a much higher EC value for FSL, which suggests a larger number of smaller clusters, which again supports why there was no activation in this software package. So going back to the original question of analytic flexibility, the results we've got really show evidence that this flexibility is high, and we've seen that in disagreement on where there is significant activation, the low dice coefficients for the cross-software comparisons, the cloud of bland Altman plots, and the differences in the Euler characteristics I just showed. So going forward, we want to apply these measures of metrics to each stage of the pipeline as a further way you could explore this. So thank you for listening. It's been a pleasure to talk to you today.